In this video, we're going to be talking about related rates, which is used for finding a rate of change from other known rates of change. Okay, so to understand how to solve a related rates problem, you need to first understand what is a related rate and when do you use it. So a related rate is an application of the derivative where the instantaneous rate of some known variable is used to find the instantaneous rate of change of an unknown variable. For example, if you are given the position function, which would be 16t squared minus 6t, you have to take the derivative of the position function to find v of t. And v of t would equal 32t minus 6.
Our example is, if a balloon leaves the ground 300 feet away from you and rises vertically at a rate of 120 feet per minute, at what rate is the angle of inclination of your line of sight increasing the instant the balloon is exactly 300 feet above the ground?
So, what we need to solve this problem is a few key factors. We need to know what's given. We need to know what we want or what we're looking for, what we're solving for. And we want to know when we want it. So these would be the three key factors that you look for anytime you're doing a related rates problem. Now, according to our problem, our given would be a variable we call dh dt, which is known as 120 feet per minute. And then what we want would be d theta dt. We're going to put a question mark because we don't know what it is. And when we want it is at h equals 300 or when the height is equal to 300 feet. All right, so over here you see I've kind of condensed the variables. And right now I'm about to draw a little snapshot picture, which you should also do anytime you solve a related rates problem. Now, according to the problem, we're going to say you, the watcher, or the viewer, or whatever. You're standing here, away from the balloon. You're 300 feet away from where the balloon is rising. So the balloon is rising. Here's our balloon. It's all cute and stuff. Okay. And this is our variable h. Now we don't know h. We only know what we want the height to be when we find d theta dt. But we do know dh over dt, which is, again, as we've said up here, 120 feet per minute. Okay, so essentially what we're going to do is we're going to set up an equation. I'm sorry. I forgot to draw my angle there because we're trying to find the rate at which the angle of inclination is increasing. So we're going to set up an equation. We have h and we have 300 feet. We know that across from the angle, that's the opposite side, and next to the angle, that's the adjacent side. And according to our trig facts, opposite over adjacent would be the tangent. So once we plug in the opposite and adjacent values, we get the tangent of theta is equal to h over 300 feet. So we have our equation, tangent of theta is equal to h over 300 feet. In order to use this equation, we need to know what we're solving for. So we go back to our little information section and we look at the want. And what we want to solve for, or what we want to know, is d theta over dt when the height is 300 feet. And we've made a little note that theta is equal to pi over 4. So in order to solve for d theta over dt, we must take the derivative of both sides. On the left side, we take the derivative of theta with respect to t. as you see in this step here, and we end up with d theta over dt. On the right side, we pull out the constant 1 over 300, and we take the derivative of the variable h with respect to t, and we end up with dh over dt. Now, in order for us to solve for d theta over dt, we must isolate it, or essentially get it by itself. So we divide the left side by secant squared of theta, and on both sides, and then we end up with d theta over dt is equal to our right side, where we have plugged in dh over dt, which has been given to us as 120 feet per minute times 1 over 300 feet, all over secant squared of theta, which is pi over 4. So now that we plug everything in, we end up with d theta over dt is equal to 120 feet per minute times 1 over 300 feet over 1. And we simplify the numerator, canceling out the feet, leaving us with minutes. And our numbers get simplified until we end up with 2 over 5. In the denominator, we simplify secant squared of pi over 4, knowing that secant is also equal to 1 over tangent. We plug in pi over 4 and square the whole thing, and we end up with 1. And this leads to us ending up with 2 over 5 times 1 over the minute. And because it's angles, or we're dealing with an angle, we use radians, and we end up with 2 over 5 radians per minute as our final answer.